He's trying to think of a word. Yeah, I can't think of a word.
All right. Today, today we are going to start talking about rational functions. Okay, this is probably going to be a 2-day lesson here. So a rational function is just whenever I have a polynomial divided by another polynomial. Okay, that's a rational function. So the first thing that we want to do, this is actually a review, is talk about the domain of these types of functions. Right? We talked about domain in the last chapter. So domain of a polynomial is all real numbers, right? But what happens when I have a denominator? What do I need to look for? What are places where the domain would not be defined? Or what equals 0? Right? Wherever the denominator equals 0 will be places that are not included in the domain. So find the domain of each of these rational functions. What we want to do is figure out where the denominator equals 0. So I'm going to say 3x plus 2 cannot equal 0. And so I'm just going to solve this, subtract 2 over, and then divide by 3. We get that x cannot equal negative 2/3. It can equal anything else except negative 2/3. So how do I write that in interval notation?
Negative two-thirds. Yeah. No, it's not a bracket, it's parentheses.
It's going to be a parentheses, so not including it.
Negative 2/3.
Right, to skip one value, this is how we do it. Okay, put that value with parentheses, then union, parentheses, starting at that same spot. Okay? You guys try the second one. Find me the domain of this.
Which one puts on top?
About
expect.
yes.
You tell me. Are there two numbers that multiply to 8 that add to negative 6?
No, it's impossible.
I'm sure there are.
It's impossible.
There's gotta be one.
I always doubt Mr. Fatch.
I'm sure it is.
Mr. Fatch, what day?
Actually, I don't.
What? Get out. Mr. Fetch, what if I told you to leave, but then you actually left and didn't come back? I would be pretty sad. Then you'd just be my dad, part 2.
Plus or minus 3? Six plus 4.
What?
So to solve this, right, you can use, this one does actually factor, okay, but I use the quadratic formula instead. So again, you can solve a quadratic however you want. We should get 2 values, right, that make the denominator 0. So when we write our domain, we would start at negative infinity. We can go all the way up to 2. Does it matter which one I use first, 2 or 4 here? Yes, the smallest value would always go first, right? So negative infinity up to 2, union that, 2 to 4, and then union 4 to infinity. Now, what if quadratic in the denominator that yielded imaginary answers. It's fake. So yeah, what if? Let's see. I don't know. Let me just make up another one here. What if we do like 4x over x squared plus 4? Okay. What values of x would make the denominator equal to 0? Right? That's what we're trying to figure out here. Imaginary numbers actually have a lot of applications to electrical currents. That's probably the most practical application, and it sounds like I don't know, but I mean that's the most practical application that I've ever seen. Is you use imaginary numbers to figure out electrical currents. I don't think you're going to get into it. You're not going to get into that. I mean, we can get into it. His brake light.
So electricity brake light. So if someone asks me, I'll be like, it's not electricity.
What? So back to this example that I just made up here. If I set my denominator equal to 0 here, say x squared plus 4 cannot equal 0, we're going to get imaginary numbers. And if I subtract the 4 over, take the square root, we get x cannot equal plus or minus 2i.
Yeah.
Should I then write my domain as negative infinity up to negative 2i, skip 2i, then negative 2i to positive 2i?
I don't know about that.
Why not? They're fake. When we're talking about the domain, we're talking about real numbers.
So,
right?
Would you just skip over it?
Yeah. If we're thinking about values that make the denominator equal to 0, we're talking about real numbers that make the denominator equal to 0. So if I get imaginary answers like this, that means that all real numbers will be included in the domain. Right? All real numbers would be included in the domain. There's no real number I can plug into the denominator here to make it equal to 0. So when that happens, the domain is just everything. Negative infinity to infinity. If all you get are imaginary numbers, yes, the domain will be negative infinity to positive. That's great.
So if you see it like setting up to be an imaginary set of solutions, would you just do that?
Yeah. Any questions on domain? No. All right, so let's talk about asymptotes then. Okay, I think today we'll just get to look at vertical asymptotes. But first, let's just define an asymptote in general. Okay, so an asymptote is a vertical or horizontal line. Okay, we can have both vertical and horizontal asymptotes. Vertical or horizontal line that the graph of a function approaches. Okay, it's just a vertical or horizontal line that the graph of a function approaches. Okay? So to find vertical asymptotes, we want to first, I guess there's really two steps here. Okay, the first is cancel out any common factors between the numerator and denominator.
That's exactly what I was thinking.
And then, after we've canceled out any common factors, then we set the denominator equal to 0. Okay, so it kind of looks like places wherever the denominator equals 0, we're going to have an asymptote. Okay, but that's not quite true. Okay, we'll look at an example here in a second. Actually, let's skip the whole here and jump down to look at a couple examples of at A and B first, and then we'll come back to the whole. So to find vertical asymptotes, first, to cancel out any common factors. So if I'm looking at the first one, 1 over x plus 7, well, there aren't any common factors between the numerator and denominator, right? So I just go to step 2, set the denominator equal to 0. So x plus 7 equals 0, subtract the 7 over, and I get x equals negative 7. So we want to write our asymptotes as equations of lines. Okay? Well, this is the equation of a vertical line. Okay? X equals negative 7. And we'll talk about graphing these tomorrow, but what that means is I'll have a vertical line that the graph approaches from both sides, okay, at negative 7. So, same idea for B here. Okay. On this one, again, there are no common factors that I can cancel out between the numerator and denominator, but I do want to factor the denominator. Okay, I want to see what factors I'll get. So how does x squared minus 25 factor? X minus 5, x plus 5. It's the difference of squares. So if I set each of those equal to 0, we would say, well, x equals 5, and x equals negative 5 will be equations of my asymptotes. Yeah, so if instead we wanted to just say x squared minus 25 equals 0, solve that by adding 25 over and taking the square root, we get the same thing. Yes, because of what we're going to talk about next. So yes, you do always want to factor. So for vertical asymptotes, if nothing cancels out between the numerator and denominator, the top doesn't matter. All right, so let's jump down. Well, yeah, let's talk about C here. So on C, again, there are no common factors between the numerator and denominator. Right? I've got 7 over x squared plus 1. So then I just want to think about, well, if I set the denominator equal to 0, and solve, I'll get my vertical asymptotes. So subtract the 1 over, take the square root, and I'll end up with x equals plus or minus I. But we are only talking about real numbers, right? We can only have x equals a real number to be a vertical asymptote. It doesn't make sense to have an imaginary number as a vertical asymptote. So what that means, okay, again, like we talked about the domain, if we get imaginary numbers at the end, that meant there were no domain restrictions. It also means there would be no vertical asymptotes. Right? So for this graph, there are no VA. Okay? We can just abbreviate vertical asymptotes as VA. So now something a little bit different is going to happen on D. Okay, remember the first step is to cancel out any common factors. Well, to do that, I have to be able to see all of the factors. So we want to factor everything that we can. X minus 3 doesn't factor, but how does x squared minus 9 factor? X minus 3x plus 3. Right? It's another difference of squares. So we can actually cancel out these factors of x minus 3. I remember a factor is just something that's being multiplied. So I can cancel out these x minus 3's, and this just becomes 1 over x plus 3. Okay. Now, after I've canceled out any common factors, now I set the denominator equal to 0 to find vertical asymptotes. So, we just get x equals negative 3 as a vertical asymptote. Now, what happens at positive 3? Okay, it's not a vertical asymptote because I was able to cancel it out. But what does happen is we will end up with a hole here. Okay, we will end up with a hole at x equals positive 3. So whenever I can cancel a factor out like this between the numerator and denominator, there will be a hole in the graph. Okay, so I don't know exactly what this graph looks like, but what I do know is I'm going to have a vertical asymptote at negative 3. So, I don't know, maybe this looks something like this. But then I also know that at positive 3, I'm going to have a hole. So whatever this graph does, I'm just going to have a hole there. Okay? It's not going to be an asymptote. It's just going to be an open circle at that point. Okay? And we'll get into graphing the rest of the function tomorrow. But for now, we're saying wherever we have a factor that can cancel out, that's what will happen. We will just have a hole at that value. Okay? So back up at the top there. Okay, we can fill in that spot under hole. Okay, we can say there will be a hole wherever a factor cancels between the numerator and denominator. So, to find vertical asymptotes and holes, factor everything, cancel out any common factors, and then set the denominator equal to 0. So, let's do one more here. So on E, if I factor the numerator, how would that factor? I don't think the numerator factors into x equals 1. So I want two numbers that multiply to negative 2 that add to positive 1. And I think we would have x plus 2 and x minus 1, right? Over x plus 2. So I can cancel out these x plus 2's. So what happens then at that factor? There's a hole. There's a hole at what value? At negative 2. So we can say there's a hole at x equals negative 2.
Well, but then there's just a 1 on the bottom.
Well, I've got x minus 1 in the numerator. I have nothing left in the denominator.
So does that mean there's no asymptote?
That means there's no vertical asymptote. Okay? So yeah, be careful here. This x minus 1 that's left over is in the numerator. It's not in the denominator. You would only set whatever's left in the denominator equal to 0. So this has a hole at x equals negative 2 and no vertical asymptotes.
I enjoyed that one.
Okay. Any questions?
No.
Dude,